This presentation summarizes efforts within AI Speak project toward development of visual speech recognition module. The process of human speech production is bimodal. It consists of both audio and visual component. Visual component includes movement of lips, tongue, jaw, and facial muscles, while audio component produces an audio wave. The process of speech perception is also bimodal as confirmed by evidence from literature. One of the most known is so-called McGurk effect, presented in paper Hearing Lips and Seeing Voices. In an experiment presented in this paper, subjects were reproduced sound ba, while being shown with a video corresponding to sound ga, and they often perceived new third sound da. There are also evidences that older adults with age-related hearing loss often exhibit enhanced audio-visual integration, using visual cues like lip reading more effectively to compensate for degraded sound. The process of automatic words decoding based only on video modality is called visual speech recognition and is often denoted in literature as lip reading. The process of lip reading is a highly challenging task, even for humans, particularly when linguistic context is limited. One of the main difficulties arises from the lack of one-to-one correspondence between phonemes, which are the fundamental units of spoken language, and visemes, which represent the visual configuration of the speech articulators. In many cases, two or more phonemes are mapped to a single viseme, making visual discrimination inherently ambiguous. Examples for the Serbian languages are illustrated on the slide. The video shown above corresponds to the pronunciation of the Serbian phoneme P, while the video below corresponds to phoneme B. Despite the acoustic difference between these phonemes, their visual appearance during articulation is very similar. In automatic lip reading, additional challenges are introduced, such as variations in illumination, speaker pose, and background conditions. For this reason, a large-scale and diverse datasets are essential for the development of robust and high-quality visual speech recognition systems. Standard lip reading architectures are typically composed of several key building blocks. The process usually starts with a pre-processing stage where the face and lip region are detected and then normalized. This step helps reduce variability caused by differences in position, scale, or lighting conditions. Next, a feature extraction module is applied. In modern systems, this is most often implemented using convolutional neural networks or their variants, which are well suited for learning spatial patterns from visual speech data. Since speech is inherently dynamic, temporal modeling is then required to capture motion over time. This is commonly achieved using recurrent neural networks such as LSTM or GRU, or more recently, transformer-based architectures. Finally, the decoding stage is frequently based on connectionless temporal classification, which allows the model to produce a sequence of output symbols without explicit frame-level alignment. An example of widely adopted architecture that represented a major breakthrough in visual speech recognition called LipNet, which is shown on this slide. At the time the project was proposed, there were no publicly available resources for lip reading in Serbian languages. As a result, one of the initial activities of the project was the creation of the AI Speak corpus. This corpus is bilingual Serbian-English dataset recorded in strictly controlled environment. It consists of recordings from 25 speakers in both languages. For each language, every speaker recorded the alphabet, 4 groups of fixed words, 25 sentences that are identical across all speakers, and an additional 50 sentences that are unique to each speaker. Overall, this amounts to approximately 10 minutes of audio-visual material per speak per language. In later stages of the project, the focus shifted toward the development of larger and more diverse corpus. This was achieved by incorporating audiovisual material available online, such as podcasts, news, broadcasts, in order to better capture real-world variability. Our initial efforts in lip reading are presented in the current slide. Since the development of spontaneous and continuous speech lip reading system requires a large amount of high-quality data, significantly more than what we initially collected, we began with a simpler and more controlled approach. Based on the AI Speak corpus, we constructed an additional artificial dataset by concatenating isolated words extracted from the original recordings. Each sentence in this dataset follows a fixed structure of the form: command, phoneme, direction, phoneme, day, number, where the command, direction, day, and number are selected from predefined word sets. For this experiment, we employed the previously mentioned LipNet architecture, which was originally trained on the grid corpus and is well suited for the sentence structures similar to those in our artificial datasets. The results are summarized in the table shown on the slide. Two speakers not used during training, one male and one female, were selected for evaluation. Without any post-processing, the model achieved a character error rate of 15% and word error rate of 44.6%. After applying a language model tailored to our dataset, the character error rate improved by additional 3%, while the word error rate was reduced by approximately 9%. Further analysis revealed that many errors were related to the recognition of isolated phonemes, which appeared twice in each sentence. This behavior is expected, given the previously discussed ambiguities associated with visence. When phonemes were excluded from the word error rate calculation, the VER dropped to 13.2%. We have also developed a simple application for testing our model, which we will demonstrate shortly. Here is an example of test data.
Potvrdi L napred J petak 1.
And now we will run the inference using our app and trained model. As you can see, the whole sentence was successfully recognized. We will also test on another example.
Početak U napred v utorak 3.
And now the inference. As you can see, the model made two errors. One, when the F was recognized instead of V, which are kind of similar phonemes in Serbian, and there is an error on the last word in this sentence. In future work, we plan to further extend this application by enabling recognition for video recording directly using a webcam. However, to achieve this, the current model will require fine-tuning, as the resolution and recording conditions in real-life scenarios differ significantly from those in our existing dataset. To address this challenge, we have already began collecting a lower quality dataset recorded using standard webcams, which will be used to adapt the model to more realistic conditions. Thank you for your attention.